Hello students, in today's lecture we are going to learn about waves. In this lecture we will cover NCERT section 14.1 to 14.2. We will also solve an example 14.1. This is our disclaimer. Strategy for competitive exams. So to develop good problem solving skills we should master fundamental wave properties, wavelength, frequency, amplitude, and wave speed relationships. Focus on superposition principle and interference phenomena for complex wave interactions. Practice wave equations and their solutions across different boundary conditions. Study standing waves, normal modes, and resonance phenomena thoroughly. No reflection transmission of waves at boundaries and beats phenomena. Understand wave speed variations in different media and Doppler effect applications. Solve problems from past year JEE and NEET papers. For recommended books, visit our website forum.porter.ai to get the suggestions of books and guidance. Learning objectives. Now let's see what you will be able to understand by the end of this lecture. By the end of this lecture, you will be able to understand waves and differentiate between mechanical and electromagnetic waves. Classify and explain the properties of transverse and longitudinal waves. Alright, this is our index. So in today's session, we will cover first 14.1 introduction, then 14.2 transverse and longitudinal waves, and last we will solve an example 14.1. Let's start by introducing waves. So let's define what a wave is. A wave is a disturbance that moves or propagates through a medium, but it does this without actually moving the material itself from one place to another. Alright. So the disturbance travels the particles of the medium, like water molecules just oscillate or move back and forth in place. They don't travel along with the wave. Examples of wave. Ripples on water where cork pieces moves up and down but not outward. This shows us that the disturbance the wave moves outward, but the water and the cork stay in roughly the same place. So demonstrating that the disturbances moves, not the water itself. So look at figure. Ripples moves up and down in water. Alright. Example of waves. Sound is a great example of a wave. Sound travels through air, but the air itself does not move from the source to your ear. Instead, the disturbance moves through the air, where disturbances in air travel without air flowing from one point to another. The key point is that the disturbance or the energy moves forward, but the air molecules themselves just oscillate around their positions. This is why you can hear someone talking across a room without the air itself flowing from them to you. Now let's introduce the different types of waves. Based on the orientation of particle, motion and direction of energy, there are three categories. First, we have mechanical waves. These waves need a material medium like air, water, or a solid to travel through. Second, electromagnetic waves. Unlike mechanical waves, electromagnetic waves do not need a medium. They can travel through empty space. Light, radio waves, and X rays are all electromagnetic waves. And last or third, matter waves. Matter waves describe the wave like behavior of particles such as electrons. This concept is important in understanding things like electron microscopes and the behavior of atoms. Alright. Now let's understand mechanical waves in details. So these waves require a material medium for propagation and cannot travel through a vacuum. These waves are created by an initial energy input which causes particles in the medium to oscillate. This energy causes the particles in the medium like water molecules or air particles to start oscillating or moving back and forth. Now let's look at some specific examples of mechanical waves. The first example is ripples on a pond surface. When you throw a pebble into water, the disturbances spreads out as waves in outward direction. Alright, here the water acts as the medium and the energy from the pebble causes the water particles to move up and down, creating visible ripples. Another common example is sound waves traveling through air. When you speak, your vocal cords vibrate and push air particles, creating compressions and rarefactions that move through the air to your listener ear. Without air, like in a vacuum, sound cannot travel at all. A third example is seismic waves traveling through the earth. These are the waves produced the ground causing the earth's particles to vibrate. So to sum up, mechanical waves always needs a material medium like water, air or rock to carry the energy from one place to another. Now look at a schematic diagram of a mechanical wave. This figure shows a typical wave pattern. Alright. So there is a uh, displacement in meter, crest, trough, amplitude, rest position and times. Let's see. So let's see all part one by one. First, the highest point. The highest point on the wave, this is called the crest. The crest is where the displacement of the medium is at its maximum above the equilibrium position. For example, in a water wave, the crest is the top of the wave you see. Alright. Next, look at the lowest point on the wave. This is known as the trough. The trough uh, is where the displacement is at its maximum below position. In a water waves, this would be the lowest dip between two crests. Amplitude. Amplitude is the maximum displacement from the equilibrium position to either the crest or the trough. It tells us how tall the wave is. And next is wavelength. Wavelength is the distance between two successive crests or two successive troughs. It's usually measured in meters. For instance, if you measure from one top of one crest to next, that's one wavelength. All right, this one. Now we are moving on the electromagnetic waves. This is a major category of waves in physics, and it's important to understand how they differ from mechanical waves. First, unlike mechanical waves, these waves do not require a medium and can travel through a vacuum. Alright. Electromagnetic waves travel through a vacuum at a constant speed, which we call c. And the value of c is c equal to 299792458 meter per second. This is a fundamental constant in physics, and it's the fastest speed anything can travel. Examples: light waves coming from stars. Light from stars is a great example. Alright, since it travels millions of kilometers through space to reach us. Alright, so this is important. Other types of electromagnetic waves include radio waves, microwaves, infrared, visible light, and ultraviolet, X-rays, and gamma rays. All of these are part of the electromagnetic spectrum. Alright. So, the spectrum is this one. Figure electromagnetic waves. Electromagnetic waves are unique because they don't need a medium and always travel at the speed of light in a vacuum. I think this is clear. Alright. Now let's understand matter waves. Concept of matter waves says that there's a wave associated with moving particles like electrons and protons. These waves are observable at microscopic level. At macroscopic level, like for a baseball, these waves are not observable. Alright. So, in this chapter, we will focus on mechanical waves which require a medium to travel. Now, let's see waves with harmonic oscillations. Let's start by looking at waves in elastic media. Elastic media are materials that can stretch or compress and then return to their original shape, like stretched strings, coiled springs, or even air. All these systems can undergo harmonic oscillations, which means they move back and forth in a regular pattern. Alright, motion is the foundation for how waves travel through these materials. Next is spring oscillation. So imagine a collection of springs connected in series, like in the figure shown here. Springs connected in series. Each spring is attached to the next, forming a chain. This setup helps us visualize how a disturbance can move from one part of the system to another. Suppose we suddenly pulled end A of the first spring. This action changes the equilibrium length of that spring, meaning it stretches or compresses uh, away from its natural resting position. The equilibrium position is simply where the spring would be if no force were acting on it. By disturbing the first spring, we set the whole system into motion. So, this initial disturbance does not just stay in the first spring, it causes the second spring to stretch and compress as well. In other words, the energy from the first spring is transferred to the next one, and so on. As a result, these disturbances travel from one end of the spring system to other, causing each spring to oscillate around its equilibrium position. This is the essence of wave propagation. Energy and motion move through the medium, even though the individual particles or springs mostly move back and forth rather than traveling with the wave. Alright, now let's discuss two types of mechanical waves. Based on the direction of oscillation of particles of the medium, waves are classified into two types. First, transverse waves. In transverse waves, the particles of the medium move at right angles or perpendicular to the direction of wave travels. A good example is a wave on a string, where the string moves up and down while the wave moves horizontally. Light waves are also transverse, although they don't need a medium. Second type is a longitudinal waves. The particles of the medium move back and forth in the same direction as the wave travels. Sound waves in air are a classic example. Air molecules vibrate back and forth as the sound waves moves forward. Alright, so let's discuss transverse waves. This is one of the main types of waves. In a transverse waves, the particles or constituents of the medium move back and forth at right angles or perpendicular to the direction of the wave is traveling. If we talk about the example, so we can say if the wave moves left to right, the particles move up and down. This perpendicular motion is what sets transverse waves apart from other types like longitudinal waves. Alright, the oscillations, look at figure transverse waves. The oscillations can be in any direction within a plane that is perpendicular to the direction of the wave travels. Alright, so look at the diagram, see how the wave moves horizontally, but the particles moves vertically. The direction of motion and direction of oscillation. Some common examples of transverse waves include waves on a stretched string, like when you pluck a guitar string, and light waves, which are electromagnetic. These examples show how transverse waves appear in both mechanical systems and in electromagnetic phenomena. Alright, now let's understand a transverse mechanical pulse travels along a stretched string. So image shows a single localized disturbance, the bump, propagating along the string rather than a continuous wave. Figure 14.2, pulse traveling in a stress string. So now what causes this pulse? As soon as we give energy to the string, even for just a moment, the particles of the string start to move. This energy inputs makes the spring's particles oscillate or back move back and forth, but only for a short time and in a specific region. The particles of the string moves up and down, which is perpendicular to the direction of the pulse is traveling. So if the pulse moves along the x-axis, the particles themselves move along y-axis. This we call a transverse pulse. The disturbance is at right angles to the direction of travel. So because we only give energy to the string for a brief moment, we get a single pulse instead of a continuous wave. If we kept seeking the string, here we would create a continuous wave, but here the disturbance is just a one time event. All right, now let's look at have a sinusoidal wave travels along a stress string. So first imagine an external agent like your hand moving one end of of a string up and down in a smooth, continuous and regular way. This motion is called sinusoidal because it follows a sine wave pattern, which means the movement repeats in a predictable cycle. Alright. As a result of this continuous up and down motion, a disturbance travels along the string. This disturbance forms a sinusoidal wave, which means the shape of the wave matches the sine function. So looking at figure 14.3, we see a transverse wave, specifically a harmonic or sinusoidal wave, moving along the stress string. Alright, the term harmonic means the wave has a regular repeating pattern. Point out that a wave in a transverse wave, the particles of the medium move at right angles to the direction of the wave's travels. In both the case of a single pulse and a continuous sinusoidal wave, elements of this string oscillate about their equilibrium mean position as the wave or pulse passes through them. Alright, the equilibrium position is where the string would be if there were no wave. It's a resting point. So this oscillation is what allows the wave to transfer energy along the string without the string itself moving forward. Now let's discuss longitudinal waves. In longitudinal waves, the constituents of the medium oscillate along the direction of wave propagation. So particles of the medium are moving back and forth parallel to the direction of the wave is traveling. Alright. So compressions are areas where the particles are crowded close together, while rarefactions are where they are spread apart. As the wave moves, we can say these regions travel through the medium, carrying energy from one place to another. This pattern of the compressions and rarefactions is what allows sound to travel through air. The figure given so the compressions and direction of propagation. Clear? For examples, sound waves in a air are classic longitudinal waves. Another example is the wave you see when you push and pull a spring along its length. So whenever you hear a sound, remember it's a longitudinal wave moving through the ear to your ears. Clear? Now let's understand how longitudinal sound waves are generated in a pipe. A long pipe is filled with air and a piston is placed at one end. Figure 14.4. Longitudinal waves are sound generated in a pipe filled with air by moving the piston up and down. Now, if we give the piston a quick push forward and then pull it back, we create what's called a pulse. This pulse is a single disturbance that travels through the air in the pipe. As the piston moves, it creates areas where the air molecules are pushed closer together, called regions of higher density or condensations, and areas where they are spread further apart, called rarefactions. These altering regions move down the pipe as wave travels. Now, uh, if the piston moves in and out in a continuous and periodic way, meaning it repeats the same motion over and over, like a sine wave, it produces a continuous sound wave. The figure 14.4 here shows the piston at one end of the pipe moving up and down to create these waves. Emphasize that this regular motion is what makes the sound wave steady and predictable. Now let's focus on what happens to the air inside the pipe. The air particles or volume elements start to oscillate, which means they move back and forth. This back and forth motion is caused by the piston pushing and pulling on the air, and it's what actually carries the sound energy through the pipe. And it's important to note that these oscillations happen in the same direction as wave is moving, that is parallel to the direction of wave propagation. This is what defines a longitudinal waves. Clear? As opposed to a transverse wave where the motion is perpendicular. So in sound waves like these, both are the particle motion and wave travel in the same direction. Example 14.1. Given below are some examples of wave motion. State in each case if the wave motion is transverse, longitudinal, or a combination of both. A. Motion of a kink in a longitudinal spring produced by displacing one end of the spring sideways. Waves produced in a cylinder containing a liquid by moving its piston back and forth. Waves produced by a motorboat sailing in water. And D. Ultrasonic waves in air produced by a vibrating quartz crystal. Alright, let's look at the solution. For part A, when we move one end of a spring sideways, we create a kink that travels along the spring. This is a transverse wave because the movement of the spring coils is at right angles to the direction of wave moves. So, in a transverse wave, the displacement of the particles of the medium is perpendicular to the direction of the propagation. When a kink is produced, the displacing one end of a longitudinal spring sideways. So when we create a kink by moving the end of the spring sideways, the coil move up and down or side to side while the kink travel along the spring. This perpendicular relationship between displacement and the wave direction is what defines a transverse waves. I hope this is clear. Now, B. When we move a piston back and forth in a cylinder filled with liquid, it creates compressions and rarefactions. Compressions are regions where the particles are pushed closer together, and rarefactions are regions where the particles are spread out. This is a characteristics of a longitudinal wave. So, wave produced in a cylinder containing a liquid by moving its piston back and forth are longitudinal waves. Now, see, waves produced by a motorboat sailing in water are actually a combination of both transverse and longitudinal waves. This means that the water particles move both up and down, transverse and back and forth longitudinal as wave passes. So, water waves involves both vertical and horizontal displacements of the water particles. As the wave moves, each water particles follows a roughly circular path, combining both up and down and back and forth motion. This is why we say water waves are a combination of transverse and longitudinal waves. Now, let's see D. Ultrasonic waves in air are an example of a longitudinal wave. That means the vibration of the particles in air move back and forth in the same direction as the wave travels. Ultrasonic waves, just like ordinary sound waves, are pressure waves. This means they travel by creating regions of high and low pressure as they move through the air. The energy is carried by these pressure changes, now not by the movement of air from one place to another. In longitudinal waves like these, the air particles vibrate parallel to the direction of wave moves. So if the wave is moving to the right, the air particles also move back and forth to the right and left. This is different from transverse waves where the vibrations are at right angles to the direction of travel. Now let's summarize what we have studied in this lecture. A wave is a disturbance that transfers energy and momentum through a medium without material support, where particles oscillate about their equilibrium positions. Common examples include water ripples, sound waves, and electromagnetic waves. Transverse waves. Particles oscillate perpendicular to wave propagation direction. Only propagate in media that can sustain shear stress. Example, a string vibrating in y direction while wave travels in x direction. Longitudinal waves. Particles oscillate parallel to wave propagation direction. Can propagate in any medium with bulk elasticity, solids, liquids, gases. Characterized by compressions and rarefactions. Example, sound waves in air. Some wave phenomena like water waves from motorboats can exhibit both transverse and longitudinal components, making them combination waves. The type of wave motion depends on the both of the source of disturbance and the properties of the propagating medium. We have some practice questions. These questions will enhance our concept and problem solving skill. So please solve. First, and homework. This is homework. First, what is a wave? Second, what are the types of waves? Next one, can mechanical waves travel through vacuum? What are known mechanical waves? What are the types of mechanical waves? So these are the practice questions. Clear? Thank you for your attention. I hope this lesson was helpful.